geomechanical logs from CT scans. CT scans are images, and synthetic geomechanical logs are the data that you want in the subsurface. So from surface, you want to predict subsurface data. And in the last webinar, I kind of put forth why we are doing this, how we are doing this. I kind of laid out the entire plan. So I will not repeat the entire thing, but I'll give you a quick review of what we discussed in the last webinar. Now, this particular work was done with one of my students who is currently pursuing higher education in computer science. So I'll just go ahead. This particular work was done in collaboration with a service company. And the goal is they have a lab. In that lab, they can perform computed tomography scans. So what you see there is a CT scan image, imager. So it's a CT scan machine which can scan computed tomography. So what is computed tomography? We are trying to generate CT scans of whole cores. These are called whole, let me write it properly, WHOLE, whole core. It's a 4-inch diameter, 90 feet long section. We are performing CT scan on this entire rock. What you see here is a CT scan of a single 90 feet long Yeah, somebody is playing with my mute button, I guess. Okay, so we have a 90 feet long section, and you see the CT scan. This CT scan of 90 feet section consists of 40,000 samples. There are 40,000 images. We'll call each of these image a slice. So there are 40,000 slices, and if you combine all the 40,000 slices, you get the 90 feet description of the whole core. So this is what we have in the lab. And the goal is to use this CT scan, which is nothing but collection of pixels, dark pixels, white pixels, intermediate gray level pixels. So using all that information, we want to generate subsurface logs. And our focus is geomechanical logs: bulk density, effective porosity, horizontal Poisson's ratio, vertical Poisson's ratio, uniaxial compressive strength. We tried to generate permeability, but it didn't work. For permeability, we had NMR logs. Using the NMR logs, we had permeability. We trained a machine learning algorithm to relate the images to permeability. We did that, but it didn't work that well. What worked the best is an ML algorithm that can take CT scans, generate bulk density, horizontal Poisson's ratio, and effective porosity. So a machine learning algorithm could learn that relationship, but not the relationship with permeability. I told you what we have. We have 44,000 points at which we have measured CT scan, and it's a very high resolution measurement. Measurement was done over 90 feet. And for each of these scans that you see here, the service company generated 7 properties. For each scan, 7 properties were generated. So on the surface, in the lab, we have in total CT scan image and these 7 properties. Our goal is to generate subsurface data using this. So we have a very high resolution measurement in the lab. The problem is when we go to the subsurface. So let me show you the data that we have in the subsurface. In the subsurface, we have only 181 samples. Let me go back. We have only 181 samples over the 90 feet, which means every 0.5 feet we have a measurement. And the measurements that we have is Poisson's ratio, horizontal vertical, uniaxial compressive strength, bulk density, effective porosity, and permeability, which we will not be using in this particular work. What you're seeing here is a small subset of the entire data. Due to proprietary reasons, we don't share the entire information. So what we are sharing here is this task that can be done on only one core. We are using machine learning. We are using supervised learning. It can only get better if you give it a lot of data. These are data-driven methods. They cannot do anything if you give very limited amount of data. We don't have any limitation in the surface data. So surface data is very high resolution. We have measurements every 0.002 feet, which is very, very high resolution. So surface is not the problem. The problem is subsurface. In subsurface, we have only 0.5 feet, which means you will need a lot of logs, a lot of measurements at high resolution in the subsurface. I showed you this. This is called exploratory data analysis. You will perform simple exploratory data analysis. This looks at how are the targets, which is the goal, how are the targets related to the features. A machine learning algorithm learns the relationship of features to the target. That's the goal. What are the features? In our case, we have two types of feature. There are two types of feature. Feature one are the CT scan slices. These are the raw images. This is feature set one. And feature set two are the 7 properties that were extracted by the service companies. So we have two different types of features. And these features are at very high resolution, 0.002 feet. This is important to remember. In terms of target, this is the subsurface data. We want to predict what is the condition in the subsurface. In the targets, we have a poor resolution data, 0.5 feet. So we'll perform exploratory data analysis. There are a lot of different ways to perform exploratory data analysis. We are using Spearman rank correlation. It is looking at whether there is a nonlinear relationship between feature and target. Is there a nonlinear relationship? What kind of relationship? As long as feature increases, target should also increase. If there is a decrease in target that you see over here, that is not a monotonic relationship. So your Spearman rank correlation, it looks at monotonic relationship. If feature increases, does the target increase? And there are a lot of different types of correlation coefficient that you should look at. One very popular correlation coefficient that all of you have worked with is R square. R square generally looks at one-to-one linear correlation, R square. To the best of my knowledge, R square is also called Pearson's correlation. What you're looking here is Spearman rank correlation. It is monotonic relationship. As the feature increases, does the target increase? As the feature decreases, does the target decrease? So you perform your exploratory data analysis, and according to that, you build your data-driven workflow. When you perform exploratory data analysis, you will know how you will clean the data, what all will you use as features, and what all will you use as target. So it's a very important step that you should never forget. I showed you this workflow. We have just started explaining the workflow. We have the data set. It has feature set 1, CT images, feature set 2, which is CT derived properties, and it has a target. So we have the target, feature set 2, feature set 1. We have the data ready. But at this level, we cannot do anything. We have to perform some feature extraction. And before feature extraction, we have to perform cleaning, pre-processing. So at the pre-processing step, as I was mentioning in the last discussion, we remove poor quality CT scans. We remove the effect of boundary. So when we have a CT scan, there is boundary, and plenty of times at the boundary, we are not doing a great job in capturing the CT scans. So we remove the boundary effect. After that, we create a feature set 1 which is useful, and we create it from CT scan images. We extract it. Then we extract feature set 2, which is more useful than the 7 CT derived properties. So we convert the CT scan images into something that is useful, which is called feature set 1. And then we convert the 7 CT derived properties into something useful, which is called feature set 2. And today's focus will be feature set 1, which is very important. And for that, we need image analysis because we'll be converting the CT scan images into something that can be used by the machine learning algorithm. And I'm pretty sure we will have time. And in there, I'll show you how we convert the CT derived properties, which is not an image, into something that is more useful. And in both the steps, you will see downscaling, which is important. We will downscale the surface measurements. So these are surface measurements, CT derived measurements, which is 0.02 feet resolution. We'll be downscaling it to 0.5 feet. Okay, why? Because at the end, our machine learning algorithm should relate 0.5 feet features to 0.5 feet target. Both features and targets should be at the same resolution so that you can use simple machine learning algorithms. I prefer using simple machine learning algorithms. I don't prefer using neural networks. Initially, when I was new to machine learning, I thought neural networks are the best. But as I'm spending more and more time, neural networks, they are not suitable for my app use. Why? Because I don't have a lot of data. Neural networks are useful for, let's say, Amazon, Facebook, Google, where there is a lot of digital data, high quality digital data in oil and gas, in the subsurface. To the best of my knowledge, we don't have high resolution, high quality digital data on which we can apply neural networks. In seismic world, maybe we'll have very high quality data, high resolution data. In my experience, most of my data is simple. They are not big data. They are smaller in size, poor resolution. So that's why I prefer using simple machine learning models. And for simple machine learning models, you first need to extract features. And when you extract features, you have to perform a suitable downscaling or upscaling so that whatever resolution you have on the side of the feature is exactly similar to the resolution of the target. So this matching of the resolutions is important because I'm using simple machine learning algorithm. If I'm using neural networks, if I have a lot of data, then I don't need to match the resolutions on both the sides. So when I talk about creation of feature set 2, I'll emphasize this downscaling. Going forward, so let me show you feature extraction 1, and then I'll come back to the other parts of the workflow. So as I mentioned, I cleaned the data. There were some CT scan slices which were broken, so we kind of removed it. Out of 44,000 slices in this 90 feet interval, almost 10,000 slices were not useful because they were broken, they were fragmented, so we removed all that. After removing poor quality CT scans, what we are left with is very high quality intact CT scans. These are randomly selected slices, and they look pretty good. What you see here is distribution in pixel intensity. And one of our hypotheses is this distribution in pixel intensity has enough information about the geomechanical property. So that's our hypothesis. Each research should have a assumption to begin with, or something that we want to prove. So here what we wanted to prove is that in these pixel intensity, which is distributed in space, both in 2D and in 3D, there is enough information that we can use to predict geomechanical properties. So with that hypothesis, we did this research. To remove the pixels from the boundary. To remove pixels from the boundary, what you need to know is you need to apply a filter that can remove this outer edge. In our case, what we did is we used a filter based on Euclidean distance. So how this filter works, we have not developed the filter. We are using an inbuilt filter that you can find in a lot of different image analysis packages. We used SK image and CV2 for this work. So you can find all these different filters. What Euclidean distance as a filter does is it assigns a value. It assigns a value to each pixel. It assigns a value to each pixel that you see here. There are plenty of pixels here. And the value is assigned based on distance from the boundary. And then we select a threshold. So let's say we select a threshold where we say anything that is at a distance greater than 10 pixels from the boundary, remove all that pixels. So what we then achieve by doing all this is a pixel intensity from the inner region. And that is very important. Anytime we keep the outer region, our performance is not that great. So now we have removed the outer edges. It's like removing the sides of a bread before you eat bread and butter, right? So we did something like that. What you see here is once we remove the edges, how does our edges look? By removing the edges, what we have here is something that is free from the edge effect or the boundary effect. Okay, time for feature extraction, which is the main part of this particular talk. And this is what I find very interesting. There are a lot of different feature extraction techniques that you can use. The easiest one, and plenty of times is the most useful, is edge detector. So there are a lot of different edge detectors that you can use. These are filters that you can apply on your image. And in your image, if there is an edge, those edges will be detected. So what you see here is coins. Coins are placed on a background. The background is, let's say, some kind of a cloth. On that, you have put the coins. So if you want to detect the edge of the coin, any edge detector will work. And as I mentioned, there are 4 or 5 useful edge detectors. The one that I generally use is called Sobel edge detector. So how does an edge detector work? An edge detector is nothing but a matrix. All of you, I'm pretty sure you know what a matrix is. It is a matrix of numbers. And what you can do is you can assign all the cells, all the units in this matrix, you can assign all of them 1. Okay. And if you assign all of them 1, and if I take this matrix and multiply it with the pixel intensity that you see here, when you do that, you will get some kind of a summation. Okay, so what I'm doing here is if there is pixel intensity, let's say the pixel intensity is 10, 10, 10, 10, 10, 10, 10, 10, 10, let's say. That's the pixel intensity in that region. And when I multiply that pixel intensity with the filter, what I'll get is for each of these cells, it will be 10 into 1 plus 10 into 1 plus 10 into 1. So it will be some kind of a multiplication and then summation. You can design a filter in a lot of different ways. These are simple mathematical transformation. So if I design a filter such that I multiply each cell by the corresponding cell, and then I add all the cells, what I'll have after applying this filter is I will get a value of 90 in this region. And then I'll apply the matrix on the neighboring region, then on the neighboring region, and so on. So I'll move the filter all across the image. Now, what a Sobel filter is something like this. A Sobel filter is something like this, where you have 1, 0, 1, 1, 1, 0, 0, 0, 0. When you apply a filter like this on an image, what, sorry, 1, 0, minus 1, 1, 0, minus 1, something like this. When you apply this filter on an image and you move on, what happens is whatever pixel intensity you have on this side gets subtracted from the pixel intensity that you have on the other side. So it's kind of a difference, and you're doing a difference over a length of 3 pixels. What is first derivative? If you remember first derivative, it is very similar. First derivative will be fi minus whatever you have over here. Let's say fj divided by the distance. Let me call that distance dx. This is the first derivative. So your Sobel edge detector, the way it is designed, the way these numbers are designed is such that when you move it across the image, it will find the edges. Anywhere you don't have edges, this minus this will be 0. If you apply it on a region where there is no edge, then whatever value you have here, whatever value you have on the other side will be subtracted and it will be 0. The same thing will happen in the vertical direction. Only when you have an edge, that's when Sobel edge detector works the best. Now, Sobel edge detector works when you have odd edges. What is odd edge? It is an edge where you have a material 1 on one side and another material 2 on the other side. So you might have a region that is white and a region that is black. And this is an odd edge. You have 2 different materials, 2 different pixel intensities on both the side of the edge. So Sobel edge detector can detect odd edge, and anytime you perform any kind of derivative, be careful of the noise. Each time you perform a derivative, you are enhancing, you're increasing the effect of noise. So this is Sobel edge detector. It helps me see the edges in the image, and I apply it on my clean slices. And when I apply on the clean slices, anywhere where I have edges will start showing up as red. Anywhere where I have weak edge, it will be yellow. And anywhere I don't have any edges, it will be black. So what I've done is by applying this Sobel filter, I've given each pixel in this image, I've given it a new value, a value that indicates whether there is an edge or not. So from this raw data, I've generated something more meaningful, and that is called feature extraction. So I'll take a short break here. If you have any questions, I can address that. What we are talking about is feature extraction so that we make something meaningful out of raw data. This is raw data, which is a CT scan image. From there, we have created something more meaningful where each pixel intensity indicates presence of edge, odd edge. If you have noise in your image, then Sobel edge detector will become useless. So ensure that there is not a lot of noise in your data. Any questions so far? Okay, so I'll go ahead. So Sobel edge detector is one feature extraction technique. The other one is Hessian region detector. It's not an edge detector, it's a region detector. Okay, and Hessian region detector is a double derivative, a second order derivative. Sobel edge detector was a first order derivative. It is looking at how does pixel change for a small distance. That is Sobel. And Hessian is looking at the double derivative. And because it's a double derivative, it is very, very sensitive to noise. So if there is noise in your data, don't use Hessian because it's a second order derivative. How does Hessian matrix work? It's exactly the same. It is some kind of a matrix, a kernel. So these things are called kernel. That's the right word. But those of you who are not new to kernel, what you can understand it as, it's a matrix. It's a matrix with some numbers. And how the numbers are designed defines how will this filter work. If you have -1 here, -1 here, -1 here, it's a very different type of a filter compared to when you have zeros on this side. If I replace these things with 0, I'm getting some other type of filter. So by changing these numbers, 1, 0, -1, or 2, -2, and so on, you will get different types of filters, different types of kernel. And for simplicity, I'm calling it as a matrix. So you'll take this kernel and you will apply it on your image, and you'll apply it everywhere in the image. And as you're applying it, you're performing some multiplication followed by some summation. So when you apply this Hessian region detector, which is second order derivative based on the kernel, what it does is when you apply the HXX filter, it will look for even edges in the horizontal direction. If you apply it in YY direction, it will look at even edges in the vertical direction. What is the even edge? Sobel detector detects odd edge. What is the odd edge? White on one side, black on the other. That's an odd edge. Hessian detector detects even edges. What is even edges? It is a edge where you have same material on both the sides. You have white on both the sides of the edge. This is a even edge, and Hessian is designed to detect even edges, but be careful. If you have noise in your data, you will see a lot of incorrect results. It is called a region detector. Because it is a second order derivative, it can detect blobs. Blobs as in some kind of a region, some kind of a region that stands out. How can it detect regions? Because it can work in XX, YY, and XY direction. So a region like this black region that you see here, that entire black region kind of stands out inside the edges. So I apply the Hessian matrix on my original raw data. And from this raw data, what I generate is XX, XY, and HYY. So now each pixel in my raw data is assigned some numbers. And these numbers represent presence of odd edges, and it also represents presence of regions. So for example, here, this blue region that you see here, this pattern that you see here, blue, red, blue. So all these patterns are indicating either some kind of an edge or some kind of region that is in this data set. Okay, so this is a second filter, which is very popular. It's a region detector, and the way it works is these numbers in the kernel are designed such that you get a second order derivative. And if I remember correctly, see, I don't design these filters, I use these filters. If I remember it correctly, the way it is designed is something like this. 1, 2, minus 1, or 1, 2, minus 1, something like that. I might be wrong, but it's a slightly different arrangement of numbers compared to the previous filter that I showed you, which is Sobel edge detector. Okay, going forward. Now, plenty of times in your image, you might have noise. So how to work with noise? What is noise? So for example, there is an image of, let's say, a letter L, L for lion, let's say. So this is letter L. And if there is any any noise in your data, what you can see is some kind of dark pixels because of the presence of noise. Having noise gives problem to Sobel and Hessian matrix. So if you have noise in your data, it's better to perform some kind of a noise reduction. And a very simple uh, noise reduction technique is simple. And again, what is simple may not work all the time, but Gaussian kernel is a very simple way to reduce the effect of noise. Okay, so what is a Gaussian kernel? A Gaussian kernel can be, let's say, a 5 by 5 matrix. It's a 5 by 5 matrix, and the numbers that you have in this matrix, the numbers are designed in such a way that if you move in X direction, you will see some kind of a Gaussian distribution. If you move in Y direction, you will see another Gaussian distribution. So this is like a Gaussian distribution in all directions. It's a 2D matrix where the numbers are representing a Gaussian distribution. Now, what's the beauty of Gaussian distribution? This Gaussian distribution has something called sigma. Each Gaussian distribution has a sigma, and a Gaussian distribution with a very small sigma will look like this. This is called standard deviation of your data. Gaussian distribution with a large sigma will look something like this. It will have a big spread. Sigma is also known as the spread of your distribution, standard deviation, variance. So if you want to reduce the effect of noise in your data, what you do is you apply a Gaussian distribution with some spread. And when you apply a Gaussian distribution with some spread, what you're doing is you are taking some kind of an average for each region. You take some kind of an average for each region. What is the size of the region depends on the kernel that you are applying. If you're applying a 5 cross 5 kernel, it will create a different type of averaging compared to if you use a 3 cross 3 kernel. So this kernel will create an average. And the way the averaging is done is based on a Gaussian distribution. If you use a Gaussian distribution with a large sigma, if you use something with large sigma, then your image will look like this. If you use something with a very small sigma, it will look something like this. So by changing your sigma, you can change how you are performing this averaging on your real image. Your real image will look something close to this one. And by applying Gaussian kernel, you try to reduce these effects of regions that are noisy. So the effects of these regions will be removed by applying Gaussian kernel. Now there is a filter which is based on Gaussian kernel, and This is also a very popular filter. It is called difference of Gaussian, DOG, difference of Gaussian. So what it does is it applies two Gaussian filters of different sigma. So for example, here you have this Gaussian kernel and this one over here. They have different sigma. Here the sigma is 1, here the sigma is 11. You will apply these kernels on the images. You will apply them separately. And as you apply these two different kernels, as you increase the spread, your image will become blurry. When you apply something like this with large sigma of 11, your original image will become blurry. When you apply an filter with small sigma equal to 1 versus sigma equal to 11, your image will stay high resolution. You take a difference of these two images. When you take the difference of these two images, what happens is you start showing blobs, or you start highlighting regions. You start highlighting spatial regions that are different from the surrounding. And this is called a difference of Gaussian. You apply two different Gaussian filters with different sigma. This sigma is high, this sigma is low. When sigma is low, you will have less blurry image. When sigma is high, you will have a very blurry image. You take a difference, and in that difference, what you can see is blobs or regions. So that's why difference of Gaussian is also called a blob detector. If there's a butterfly and on the wing of the butterfly, you will see some patterns, some black spots, some white spots. So a difference of Gaussian can very quickly detect those regions which is different from the surrounding. So this is difference of Gaussian. This is a blob detector. There are other types of blob detectors. What I showed you is difference of Gaussian. Difference of Gaussian is approximation. It's approximation of Laplacian of Gaussian. So this is a very, very accurate blob detection technique, Laplacian of Gaussian, but it is computationally very expensive. Something that is generally good tends to be very expensive. Computational cost tends to be very high. And when you apply difference of Gaussian, it can still detect blobs. It is less computationally expensive, but it is not as accurate. It is not as accurate as Laplacian of Gaussian. Personally, I use difference of Gaussian because it does a good job in detecting blobs. It cannot detect all the blobs. Difference of Gaussian can do a good job within a computational complexity. There is another version which is determinant of Hessian, which is even faster, but it is not that accurate. Personally, in terms of blob detection, I use this one. If you have computational power, use Laplacian of Gaussian. Okay, let's take a small break. If you have any questions, we can discuss that, or else I'll just move ahead. But it is good if you have any questions, we can have a short discussion.
Yes, Professor, I have a question.
Please go ahead.
So when we were talking about removing noisy, or sorry, dealing with noisy images, we discussed a little bit about
Gaussian
sort of
kernels.
right smoothing the image
Yeah.
rather than removing outlier images. Is there or is there any system in place for, let's say you have a cross-sectional CT scan and that may just have too much noise for your data? Is there a process for identifying that image is too noisy and then removing that altogether, or do you just simply perform a smoothing um,
Yeah.
on that
So that's a
image?
great question. So what I did here, this is the right word which I didn't use, and you used it, which is smoothing, which is what I'm doing here by applying Gaussian kernel. And what you see here is 4 kernels. And here the assumption is, or not the assumption, but the way it works is when you apply larger and larger sigma, when you apply kernel with larger sigma, you will smoothen. And when you smoothen, you will reduce the effect of noise. So a high sigma kernel acts as a filter that removes high frequency variations. What is high frequency variation? In an image, if you have some spots which are noisy, this is a high frequency event. It is a noise. It doesn't occur everywhere. It's only occurs at some spots. It's like a discontinuity. So you can remove that, you can reduce that effect using a Gaussian kernel. Now let's say you want to remove all the images that have uh, such high frequency noise. Is that what your question, Gabriel? Is that
Yes, yes.
right? So see, you can do that in a lot of different ways. If I have to answer you right now, how I will do it is, this is original image. Okay, let me write it as OI, original image. I'll apply a Gaussian kernel of sigma 11. Okay, okay.
Okay,
So when I do that, what I'll get is a filtered image, and I'll take a difference. I'll take a difference of OI versus FI. If the difference is above a certain threshold, then that indicates that there is too much of noise in the data.
and then you'll use that for
Yeah, so
outlier removal.
yeah, so this is a very simple way in which I can, but I have to design it properly. I have to design the thresholds so that I can detect the images with noise. An image with noise will lead to a lot of change when you apply such kernels. But this is just one way of doing it. It's not the best way. It's not a foolproof way. There are outlier detection techniques that you can apply, but I won't go there. I won't go to the outlier detection techniques because uh, these are high. Each image is 2000 by 2000 pixels, let's say, right? So there is almost 4 million pixels in each image. So outlier detection on an image will be very difficult. So
Okay,
some kind of a smoothing, and then seeing how far is the residue from the original image. If the residue is too much, then it might indicate there's too much noise in your image to begin with. You should always think of computational time. When you work with images, computational time becomes the most important thing to take care of. Okay, any other questions?
I have a question. Is there a chance to also eliminate important information in terms of the kernel size?
So if you choose, so see, if there's no noise and if you apply a very narrow kernel, then you're not removing or you're not destroying a lot of original information, right?
Yes.
Original information stays intact when you use a kernel which is very narrow. But you're using a kernel which is spread out because you want to average things up so that you try to remove the effect of noise. You don't
Okay.
want those noisy patches to stay in the image.
Okay. And is there a chance to also like, I'm sure that I'm eliminating noise, but maybe we are also eliminating useful information from our original data.
Yeah, so the assumption is in most of the image, your useful information occurs as a bigger region.
Okay, okay.
That's the assumption. The information that is useful is generally low frequency, which means it doesn't change very
Okay,
quickly,
okay,
and
okay,
the
makes
noise
sense.
appears like the spots which are high frequency, and they come as a discontinuity.
All right, yeah.
Yeah. So the reason I showed you the Gaussian kernel here is because I wanted you to appreciate difference of Gaussian. And Gaussian kernel is one way of smoothing your data, but it's not the best way of handling noise in your data. But the reason I explain Gaussian kernel is to tell you that there are a lot of different kernels that you can design by changing the sigma, and then you can take a difference between what you get from a low sigma versus what you get from a high sigma. And when you take that difference becomes a blob detector. So you saw edge detector, you saw region detector, and now what you're seeing is blob detector. Now, one good thing about Hessian, which I forgot, is if you want to detect corners, if you want to detect intersections, if you want to detect curvature, Hessian is a very good filter. Not the best for blobs. It is not the best, but it's very good for corners, intersection, curvature, which doesn't change when you rotate the image. Intersection remains intersection even if you rotate the image. So they can detect these features, which is independent of the scaling of the feature, rotation of the feature, which is very powerful. And if you want to detect blobs or regions, the true blob detector at a low computational cost is difference of Gaussian. Okay, I think this will be the final. Yeah, I think this is the second from the final feature extraction that you can do on image. So local binary pattern, it's a texture detector. You saw edge, you saw region, blob, intersection, corner detectors, and now you're seeing a texture detector. So how does LBP work? Let me go to the next slide. So what LBP does, the way it is designed, see, all these things are algorithms, right? So the way LBP is designed is it has to give a value to that pixel, which is in red. It has to assign a value. When it assigns a value to that pixel, you are making the pixel more meaningful. Originally, you just have pixel intensity and a distribution of pixel intensity. Then you have to assign a value. You saw edge, you saw corner, you saw blob, and now it's texture. So how is texture assigned? So this pixel, let's say, has a pixel intensity of 6. Generally, in a simple image or a very basic image, you will have a pixel intensity variation between 0 to, let's say, 15. 0 means white, 15 means black. And let's say that pixel at the center in red has a pixel intensity of 6. And based on this algorithm, what you'll do is you will compare that central pixel intensity with the pixel intensity of the neighbor. So these are the pixel intensities of the neighbor. This is step one. You kind of apply a kernel. This kernel that you see here is a 3x3 kernel. You have the point of interest at the center, which is pixel intensity 6. You want to make it more meaningful. So what you do is you look at all the neighbors. Now, this neighbor has a lower pixel intensity compared to the pixel of interest, which is 6. So that's why you assign that pixel 0. The next one, 9 is greater than 6, so 1. 6 is greater than equal to 6, so 1. 1 is smaller than 6, so 0. So you kind of perform these simple comparisons, and then you assign 0 or 1. So it's a binary pattern that starts here and ends over here. It's a binary pattern, so you can multiply it with binary powers of 2 And there's some mistake here, I guess. Okay, something like this: 1, 2, 4, 8, 16, 32, 64, 128. So this is how the binary pattern evolves. So you perform this multiplication, and when you multiply, 230 is the number that you get, and you will assign the central pixel the value of 230. And then you move to the next pixel. The next pixel will be here. Then you'll move to the next pixel. You'll move to the next pixel, and so on. So you move from pixel to pixel. You look at the region around the pixel, and each pixel is assigned a value, in this case 230, based on the neighbor. You can apply LBP at a very small region of interest, or you can apply it at a very large region of interest. So there is a parameter called R, which you can change. So when you apply a large R, you're trying to detect how is this pixel with respect to its neighbor. And by doing that, you assign a value to this particular point. Now, if you look at how this LBP works, at R equal to 1, you can see very granular texture. This is the original image. There's no texture. And by performing LBP, you apply some kind of texture. Sometimes texture becomes more important than edges. So it's up to you. You have to decide for your task which is important, feature. So LBP at R equal to 1, you can apply LBP at a much broad region of interest, which is R equal to 3. We applied LBP at 2 scales, R equal to 1 and R equal to 3. We see a different texture emerging by applying these things. Now, there's no machine learning here. These are simple transformations. They are mostly statistical or mathematical in nature. Now, let's say you have an image of a pavement. So this is a pavement on which you walk. So when you apply LBP on this particular pavement, each pixel will get some value. Each pixel will get some value as you're applying LBP. And what you'll find, or what has been shown, is wherever there are edges, those pixels will have a value between 10 to 15. Where you have flat regions in a pavement, the bricks are the flat regions, the inner region. So wherever you have those inner regions, those will lie either between 0 to 5 or between 21 to 30. And the corners will lie between, let's say, 7 to 5 to 9 and 15 to 20. So your texture can also act as an edge detector or a region detector or as a corner detector. So this is a demonstration of how LBP can be used for detecting edges, corners, and flat. But the main goal of a LBP is to generate texture in an image when there is no texture. And you do that by comparing how is this pixel in comparison to its neighbor. Any questions on LBP? Any questions on LBP?
Yes, Dr. Misra, I have a question, and it's, can you get mineralogical texture based on LBP?
And see, these textures are only good if the assumptions are correct, right? So what is the assumption of LBP? The assumption of LBP is that anytime in an image, I compare pixel intensity of a pixel of interest with its neighbor, a high value will indicate that this particular pixel is higher or it's darker compared to the region, right? So if that assumption is valid for mineral texture, then you can start seeing mineral texture. But I don't think it will be valid for all the different types of mineral texture. It may be valid for certain type of mineral texture, but not all.
Okay, thank you.
What you're doing is you're making your raw data more meaningful by applying these extraction techniques. Okay, and one final thing, which is wavelet. And how many of you are aware of Fourier? I think most of you are aware of Fourier transform, right? Fourier transform. You have a signal, and you apply a Fourier transform on the signal. And when you apply the Fourier transform on the signal, this is amplitude versus time. When you apply a Fourier transform on this signal, what it detects is the frequency at which the signal is changing in time. What's the frequency of this signal? This is Fourier transform. Fourier transform is good if your signal is continuous. In an image, you might have discontinuity, right? When you detect seismic or microseismic event, you might have discontinuity. So anytime your signal has discontinuity, then Fourier transform is not the best thing. Your Fourier transform is good if your signal is continuous, and then you can apply it on the entire signal to generate the frequency at which the signal changes. Now, what if your signal is something like this? It changes like this, and all of a sudden it becomes like this, and then it again becomes so if you have discontinuity like this, a sudden change, then Fourier will generally be low in terms of its accuracy. What does a Fourier transform do? It will try to find what frequencies of sinusoidal wave, what frequency sine wave and what frequency cosine wave needs to be added so that you can accurately match the original signal. That's what a Fourier transform does. So Fourier transform will not work when you have discontinuity. Now, if you look at this image, right? Look at this image, and if you move in the horizontal direction at that level, what do you see? When you move in that horizontal direction, you see a value, let's say 0. All these white pixels are 0, 0, 0. And all of a sudden, you see a change in the signal, and then it again becomes 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? So if you move in the horizontal direction, as you move in the horizontal direction, each line is actually some kind of a signal. If you move in this direction, it will be another type of signal. You can perform Fourier transform if you want, but there is a lot of discontinuity. And because of the discontinuity, because of sudden change, wavelet transform generally works better. So that's why I prefer using wavelet transform. It is slightly more in terms of computational cost, but it is much better to handle discontinuity. So let's say there is a signal like this as you move in the horizontal direction for any given location. So what a wavelet transform does is, instead of trying to find a cosine wave or a sine wave, it will try to find a discrete wavelet. A wavelet generally looks something like this. It will try to find a discrete wavelet that can be stretched, that can be shifted to get a good match. Instead of a sinusoidal wave or a cosine wave, it will take this wavelet and it will try to stretch it, and it will try to move it so that the signal can be matched properly. So that's why wavelet transform can handle discontinuity much better. You can apply wavelet transform in horizontal, vertical, and diagonal directions. And they will tell you, what is wavelet telling you? Wavelet is telling you the rate of change, rate of change in the signal. If you see blue points here, what it means is all those regions, they have similar rate of change in intensity. If you have something which is red, it means they have similar rate of change. So it is making your data more meaningful. Okay, so Time right now is 1 o'clock. We have already crossed 1. So in the first webinar, I kind of laid out the problem statement. In this webinar, I focused more on feature extraction. In the next webinar, I'll tell you how all these features can be used for geomechanical prediction. And in our case, it is predicting the subsurface well logs. I'll show you which method works, which doesn't work, and why some methods work better than the others. If there are any questions, I'll answer it for another 5 more minutes. If no other questions, then see you the next time when we meet. Okay. Thanks a lot, Daniel and Kayla, for arranging this.
Thank you so much.
Thank
I
you.
believe there is a question in the chat, but I'm not sure if the person is still here.
If we apply Hessian filter to a seismic section in Z direction, can we change the direction of H to, for instance, HXZ and HZZ? You're talking about Hessian, right? So Hessian is a filter. It's a filter. If you want to see features in X direction, it's a different arrangement of zeros and ones. If you want to detect in Y direction, it will be a different arrangement of zeros and ones, 0, 1, and 2, and it will be a different one if you want to see it in diagonal. So for Sobel, Hessian, it's all how these numbers are arranged in that kernel, and then you apply those kernels. So you can apply it in any direction you want. You can design your own filter if you want. Sobel is first derivative and Hessian is second derivative. There are third derivative filters, which will become more noisy. You can design your own filters. And there are a lot of filters. I think there are 5, 6 very important edge detection filters. There are 3 to 4 very important corner detection filters. And I showed you the blob detection. Okay.
Sounds good. Thank you so much.
Yes. Aishwarya has a question.
Yeah, I have a question. You were talking about edge detectors, right?
So
what will happen if you apply that edge detectors to find the images that are like not
Aishwarya,
having
I don't hear you. Can you type, please?
Yes.
Yeah, there is some problem in the connection. I understand. I think you're talking from far away land. In order to get the properties, phi, density, etc., how should be the oriented CT scan related to bed dips? Yeah, that's a tough question, right? So there's a dip in the bed, and I have CT scans, and all these CT scans are horizontal. And when we take the logs, the subsurface data, they generally sense the variations in the vertical direction, and they have a depth of investigation in the horizontal direction. Dip, in my application, I don't take the dip into account. For the information about the dip, I think I need either a log that is sensitive to dip, or I need this bigger picture in terms of the seismic map. But at this level, I don't have any dip. And let me just show you, go back to the CT scan. Mostly what I see is the horizontal nature in these beds. There is slight dip here, there's slight dip here, but I'm not taking the dip into account. When I talk about downscaling, all I'm doing is I'm taking a way of averaging whatever is happening in a region and then trying to see whether that can predict a particular log or not. Let me read Aishwarya's question, which is, what will happen if we apply edge detectors to find and remove the images that are having bad edges? Something to clean. Yeah, that's a great idea, as in straight away apply edge detection here. Apply edge detection here on this CT scan. I'm just moving, yeah. So in this particular thing, you can apply an edge detector on this. And when you apply edge detector on this, what will happen is you will get a very large value all around here. You'll get a very large value all around here. And anywhere there is a large value, we can remove that. So this is one approach. We can apply edge detection. But my approach here is there is a inbuilt algorithm that can detect a strong edge like this. And from here, I calculate the Euclidean distance of all the pixels. And anything that is farther away from the edge, I'm considering that as the inner region, and I'm ignoring everything that's outside the inner region. So this is a slightly different approach, and I don't know whether edge detection will work. See, because when you apply edge detection all around here, there's a lot of wasteful calculations that is happening all around here. But that's a great insight, actually. I have to try. But again, the main focus is extracting a lot of different features and then trying to figure out which of these features are useful for our task. The next question is, how can we define optimal window size for these? Yeah, so that's a very difficult thing. So Caesar asked, how can we define optimal size, right? So for example, that's a very, very important question. And that needs a lot of domain knowledge, and it changes from task to task. So when you apply Sobel, I mentioned you can apply a 3x3, but you can also apply a 5x5. You can apply a 7x7. The same thing can happen for Hessian. And as I mentioned, for Gaussian kernel, what is the sigma? Should you use a narrow sigma? Should you use a broad sigma? When you do difference of Gaussian, you are subtracting one filter from the other. So here you have a narrow sigma, and here you have a large sigma. So what should be the large value? What should be the small value? You have to look at your images, try to see what you want to detect. Let's say if you want to detect the eyes, then maybe that will help you design your filters. And for example, LBP, when you apply different R values, you get different types of texture. So it needs a lot of hit and trial. And again, algorithm, there's nothing out of ordinary in a machine learning algorithm. Machine learning algorithm is a function. You give it features, you have a target, it will fit it. So from my point of view, machine learning or mapping is very easy. What is more important is how you design these features. And for you to design these features, you need a little bit of domain knowledge. You need to know what your task is. What do you exactly want to detect? We tried a lot of different sizes in kernel, in R, and so on. It was not easy. So as I always mention, I don't know whether I mentioned this in our last discussion. I think I did. 40% of time goes in designing or pre-processing. And then 40% of time goes in evaluating the model. And only 10 to 20% of time is spent on machine learning development. So when you develop the codes using machine learning platforms, that is 10 to 20%. A lot of time goes in pre-processing, which starts from cleaning, outlier removal, feature extraction, reducing dimensionality, which I'll show you. And then 40% of times goes in evaluating. Can you trust? Okay, I think that's it, right, for today? Or is there any other questions? Anyone who wants to unmute and ask? If not, then that's it.
I think that's it. Thank you so much.
Okay, you take care. And when is our next one?
I believe it's next week.
Okay.
So we will send all the information with all the details for sure, social media, and on each email.
Yeah, we can do it at 11 or 12. It's up to you. Just that this week I had this what do you say, an urgent meeting and I had to leave.
Okay.
As in, I could only get free after 12, but next week I'm free. Either 11 or 12 will work.
Okay, yeah, we can discuss that. Whatever
Okay.
whatever is best for you, we can leave it.
Yeah, so both is best for me, so you decide.
I think 11 a.m. was good
Okay.
for everyone.
Okay, yeah. So let's stick to the previous plan.
Awesome. Thank
Okay, you
much.
take care. Thanks, Kayla. Thanks, Daniel, and
Thank you, sir.
Jafet, right? I always
Yeah,
find your
yeah, it's Jafet. It's Jafet.
Jafet. Yeah, thank you.